Here's some of the guidelines for drawing dot structures. So let's say we wanted to draw the dot structure for this molecule, so silicon tetrafluoride. The first thing we would need to do is to find the total number of valence electrons. We would account for these valence electrons in our dot structure. So to find the valence electrons, we need to look at a periodic table. And so here I have a modified version of the periodic table. And you can see what I've done is I've kind of cut out the D block here so we can focus in on the elements that we're going to be drawing in our dot structures. It also makes it easier to see how the group numbers correspond to the number of valence electrons. For example, if we look at elements in the first group, like hydrogen, lithium, or sodium, right? The first group all have one valence electron. So the group number corresponds to how many valence electrons something has. So hydrogen has one valence electron. If we think about the periods, right? So hydrogen is in the first period, or the first energy level. So periods are going horizontally across your periodic table. Hydrogen is in group 1, has one valence electron. And if I go over here to helium, right? This would be two valence electrons for helium. And so in the first energy level, you can fit a maximum of 2 electrons. And so this is going to be important when we're drawing our dot structures, because when we're drawing hydrogen, we're always going to surround it by 2 electrons or a single covalent bond. When you get to the second period on the periodic table, so here we are on the second period, lithium has one valence electron, beryllium has 2, boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, fluorine 7, and neon 8. And so you have more orbitals in the second energy level. And so because of that, you can fit more electrons. So maximum of 8 electrons in the second energy level. And this is where the idea of the octet rule comes in. So for elements like carbon, nitrogen, oxygen, and fluorine, understanding the octet rule is going to help you when you're drawing dot structures. Now, it is possible for some of the elements in the second period to not have 8 electrons, so it's possible for them to have less than 8 electrons. So things like boron will sometimes do that. But it is not possible for elements to have more than 8 electrons. So always check your dot structures and make sure that if you have an element in the second period, you do not exceed 8 electrons. Once you get to the third period, you have even more orbitals available to you now. So in the first energy level, you have only one s orbital. In the second energy level, you have s and p orbitals, and in the third energy level, you have s, p, and d orbitals. So you can fit more than 8 electrons, and so therefore, it's possible to exceed the octet rule for elements in the third period and beyond, and we will see a few examples of that in this video and in some of the ones to come here. So getting back to our molecule, silicon tetrafluoride, if I want to find out how many total valence electrons are in this molecule, I need to find these elements on my periodic table. So I go over here and I find silicon, and I see it's in group 4. So therefore, one atom of silicon has 4 valence electrons. Fluorine is over here in group 7, and so therefore each atom of fluorine will have 7 valence electrons. And I have 4 of them, so 7 times 4, right, gives me 28 valence electrons for my fluorine. The total number of valence electrons for my molecule will be 28 plus 4. So I have to account for 32 valence electrons when I draw this dot structure. So let's go ahead and move on to the next step. Let's go back up here and look at our guidelines. So we figured out how many valence electrons we need to account for our dot structure. We don't have any kind of charges, right? So we don't need to worry about the rest of step 1 here. We move on to step 2, where we decide the central atom of our dot structure. And the way to do this is to pick the least electronegative element that we have here, and then draw the bonds. And so for our example, right, we're working with silicon and fluorine, and so we can go ahead and find those again on our periodic table. And here's fluorine, right? Fluorine is the most electronegative element, and so therefore for silicon tetrafluoride, we're going to put the silicon atom at the center of our dot structure, since it is the least electronegative of those two. So I'm going to start with silicon here, and I know that silicon has 4 bonds to fluorine atoms, so I'm going to go ahead and put in some fluorines right here. So here's some fluorines like that. So I just drew 4 covalent bonds, and we know that each covalent bond represents 2 valence electrons, right? So here's 2 valence electrons, here's 2, so that's a total of 4, 6, and 8. So we've represented 8 valence electrons so far in our dot structure. So we originally had to represent 32. So I'm going to go ahead and subtract 8 from 32. So 32 minus 8 gives me 24. So now I only have to account for 24 valence electrons. Let's go back up and look at our steps again. So let's find out where we are. So we've decided the central atom, and we've drawn the bonds, and we just subtracted the electrons that we used to draw those bonds from the total that we got in step 1. So we're on to step 3, where we assign the leftover electrons to the terminal atoms. So in this case, the terminal atoms would be the fluorines. Let's go back down here and look at our dot structure. So fluorine would be the terminal atoms. We're going to assign electrons to those fluorines, but how many do we need to assign? Well, going back to our periodic table over here. So fluorine is in the second period. So pretty good bet it's going to follow the octet rule here. So we need to surround each fluorine atom with 8 electrons. Each fluorine already has 2 electrons around it. So I'm going to go ahead and put 6 more around each fluorine like that. So each fluorine gets 6 more valence electrons. And since I'm assigning 6 valence electrons to 4 fluorines, right? 6 times 4 gives me 24, and so therefore we've now accounted for all of the valence electrons. And so this should be the final structure for this should be the final dot structure here. And so we don't even need to go on to step 4 for this molecule. This is a very simple molecule to draw. Let's go ahead and look at another example. All right, so now we have CH2O, which is the dot structure which is the molecular formula, I should say, for formaldehyde. And so for following our guidelines here, the first thing we need to do is find out the valence electrons. So we need to look and find carbon, hydrogen, and oxygen on our periodic table. So let's go back up here and let's find those elements here. So here's carbon. Carbon's in group 4, so therefore carbon will have 4 valence electrons. Here's hydrogen in group 1, so 1 valence electron. And oxygen is in group 6, so 6 valence electrons for oxygen. So let's go back down and let's calculate the total number of valence electrons that we need to represent in our dot structure. We have 1 atom of carbon, so that's 4 valence electrons. Each hydrogen is 1 valence electron, but we have 2 of them, so 1 times 2. And each oxygen is 6, and we have 1 of them, so 6. So 6 plus 4 plus 2 is 12 valence electrons. So we need to represent 12 valence electrons in our dot structure. All right, let's go back up to our guidelines and see where we are now. So we've already figured out the total number of valence electrons. Once again, we don't have any charges, so we don't need to worry about the rest of step 1. Step 2 is decide the central atom, which is the least electronegative. And remember, you are going to ignore hydrogen for this example. So if we ignore hydrogen, the central atom is either going to be carbon or oxygen. And let's look at our periodic table to figure out the relative values for those. Oxygen is more electronegative than carbon. Here we go. Here's oxygen right next to fluorine, and here's carbon over here. So remember your trends for electronegativity. Oxygen is more electronegative, therefore carbon is going to be at the center of our dot structure. So we're going to go ahead and put carbon in the center. All right, so go ahead and draw carbon, and we know that the carbon is going to be bonded to 2 hydrogens, and we know that the carbon is going to be bonded to an oxygen here. So let's see how many valence electrons we've accounted for so far. 2, 4, and 6. So we needed 12, right? We just used up 6, so right now we have 6 valence electrons left over. Okay, so let's go back up and look at the next step here. So we are to step 3, assign the leftover electrons to the terminal atoms here. All right, so the terminal atoms. Well, in this case, right, our terminal atoms would be hydrogen and oxygen, but we're not going to assign any electrons to hydrogen because each hydrogen is now surrounded by 2 electrons. And so therefore, we're going to assign those leftover electrons to the oxygen here. And oxygen is going to follow the octet rule. So it already has 2 around it, so it needs 6 more. So 2, 4, and then 6. And so that actually takes care of all of our valence electrons, right? So now we have accounted for all 12 of them. However, we're not done with our dot structure here. So carbon actually follows the octet rule almost all of the time. And let's go back up here and let's look at step 4 here. So for step 4, if the central atom doesn't have an octet, and it usually does have an octet, you can give it an octet by creating multiple bonds. So let's look at what we have so far for our dot structure, and let's see if we can create a multiple bond somehow. So if I if I took one of these electron pairs here, right, and I moved them into here, let's see what that would give us for a dot structure. Now I'd have carbon, right, with a double bond to oxygen, and this oxygen would have two lone pairs of electrons, and then these hydrogens right down here. And so this would be the correct dot structure for formaldehyde. You have an octet of electrons around carbon, you have an octet of electrons around oxygen, and hydrogen has two electrons around it, which it is happy with. So this is the correct dot structure. And let me just talk about some terminology really fast here. So these electrons in here, right, so this would be a double bond between the carbon and the oxygen. These electrons you would call bonding electrons because obviously they're involved in bonding. And then these electrons out here would be non-bonding electrons or lone pairs of electrons. So that's just terminology that you will hear people use when you're talking about dot structures. All right, so, and then let me just go ahead and highlight the fact that carbon has an octet of electrons here. So this would be 2, 4, 6, and 8 electrons surrounding our carbon. All right, let's do one more example here. Let's look at, this time, an ion. So this would be the xenon pentafluoride cation here. So we need to look and find xenon and fluorine on our periodic table, so we can figure out how many valence electrons we're dealing with here. So let's find xenon first. Okay, so here is xenon. It is in group 8, so 8 valence electrons for xenon. And then we've seen fluorine, of course, in group 7. So let's go back down and figure out how many valence electrons we need to account for here. So we have 1 xenon, and that's 8 valence electrons. Right? Each fluorine is 7, and we have 5 of them. So 7 times 5 is 35. So we have 35 plus 8 gives us 43. Now, this is actually not the total number of electrons that we're going to account for because this is an ion. This is a +1, a positive charge, which means that we lost an electron. Remember, an electron is negatively charged, so if you lose a negative charge, you have a positive charge left over. And so we're going to take away an electron. So instead of 43, we are now going to account for 42 in our dot structure. Let's go back up to our guidelines, and I'll show you where I have that written down right up here. So find the total number of valence electrons, right? And then in this case we had a positive charge in our ion, so we subtracted an electron. And then again, step 2, find the central atom, least electronegative. Okay, so we know that fluorine is the most electronegative, so that means we're going to put xenon in the center. So we'll go ahead and let's get some room right down here, and we'll go ahead and put xenon in the center like that. Bonded to 5 fluorine, so we can go ahead and put in these bonds around here like that. And how many valence electrons have we accounted for so far? Well, let's see, that would be 2, 4, 6, 8, and 10. So we had to represent 42, we just represented 10, so now we have 32 left over that we need to represent. And notice, xenon is already violating the octet rule, exceeding the octet rule. And it's okay, it can expand its outer shell because xenon is past the 3rd period on the periodic table, obviously, like what we talked about earlier. So we can go ahead and go to the next step. Now we're going to assign the leftover electrons to the terminal atoms. And our terminal atoms are, of course, the fluorines, which we know are going to follow the octet rule. And so once again, each fluorine has 2 electrons around it, so that means I'm going to give each of the other fluorines, each fluorine 6 more, right? So I'm going to go ahead and put 6 more valence electrons on each of my fluorines. And so when I'm thinking about how many how many valence electrons I've represented now, right, so I have 6 more on 5 fluorines, so 6 times 5 is 30, right? So I've represented 30 more electrons, and so that means I have 2 left over. So 2 valence electrons left over. We haven't had this situation before. Let's go back up to the guidelines to refresh your memory what we do when we have leftover electrons after step 3. So we get to step 4 here. So if necessary, in this case it is, we're going to assign any leftover electrons back to the central atom this time. And if the central atom has an octet or exceeds an octet, which is what we have in this example, you are usually done. And we're not going to worry about formal charges in this video. I'll talk about them in the next video. So we're going to take those 2 electrons and assign them to our xenon. So let's go back down here and assign those 2 extra electrons to the xenon. And so we would draw it like that. And so now we are done. We've represented all 42 of the valence electrons that we were supposed to. So you can count all those up if you want want to. Now, most people will represent this dot structure by putting brackets here and putting a positive charge outside of it. So there's your xenon pentafluoride cation. So we're gonna do a lot more examples for drawing dot structures in the next several videos and see how drawing dot structures allows you to predict the shapes of different molecules.